Okay, we're going to do variation functions now, the last section out of chapter 3. The objective here is to eventually get excuse me, check my volume, get real world situations where you can see how the functions are going to end up working and things like that. Particularly also be able to find those equations and then find particular values in those equations. There are two different and I'm going to talk about the rubrics about how you're going to grade at the end. There are two different types of variation. There is direct variation, which can be written in the form of y equals kx. Now, the x values can be squared or something like that if we need to, and where k is the constant variation. Essentially, this means as x, as x gets larger and goes to infinity, y is going to get larger. So as x gets bigger, so as x grows, y grows. Okay. Very easy example would be if you work at a job where you get an hourly rate, the more hours you work, the more money you're going to be making. Okay. As the hours go up, your money goes up. The other one is indirect variation, where it's an equation in the form of y equals k over x. You could also write it as k times 1 over x. Sometimes that's easier to do solve. Or you can also do it as x times y is equal to k. And this is part of the reason why I think I said, but if not, I'll say it now. These are based loosely. That's very much like a rational function like we did in section 3.5. And this is the opposite. As x gets bigger, y gets smaller. So they move in opposite directions. And actually, you could probably even just say it goes down to 0. My apologies. And this is actually kind of what we were doing when we were trying to find some of the asymptotes in the rational functions. As we were talking about, as x gets larger, where is the Hornell asymptote bottoming out? Okay? So, as x grows, y gets smaller. Okay? And there's lots of examples for that. So as population grows, available resources get smaller, things like that. I'm going to go through some very basic examples first, and then we'll do a couple of real-life situations, and then you guys can get turned loose on your stuff. So a couple of things as you go through here. Varies directly, so you know you're going to fall into the formula of y equals kx. And so this one, actually, there's nothing special about it. So now what you're going to do is you're going to take the data that they give you to find k. So we're going to take 20 is equal to k times x, which in this case is 4, so k is equal to 5. So the general equation is going to be y equals 5x, and then at this point you can solve out for y or for whatever they give you. They're asking for x, or they give you x, they're asking for y. So then in this case we're going to use this. So y is going to equal 5 times negative 6. So that's going to equal negative 30. It's almost like ratio and proportions problems, but not exactly. Now sometimes you're going to have, some of these things are going to be merged together. You're going to have one where it's, like here, it says supposedly r varies directly as the square of m. So we know that r, we've got this variable k out here, because that's always going to be this constant. It varies directly as m, so that means I'm going to multiply it by m. You know, it says the square of m, so I have to square it. Now notice it also says inversely as s. Okay? And that means that you have this s on the bottom, because as m is getting bigger, think about what's going on here. As m is getting bigger, r is going to get bigger because they multiply through this. You're multiplying this out. As s is getting bigger, what's going to happen is s is getting larger, you're dividing by larger and larger numbers, and that's going to drive r smaller. Okay? So now once you do this, now you plug in the information of the given that they give you. So they tell you if r is equal to 12, when m is equal to 6, and s is equal to 4, then they're going to ask you what happens when m is 6 and s is 20. So you're going to solve this out. So this is going to equal 9k, but you get 36 over 4. yeah, 36 divided by 4 is 9. So K is going to equal 12 over 9 or 4/3. So then we're going to use that and get R is equal to 4/3 m squared over s. And again, remember, you can write the K out front if you want, and that makes it a little bit easier when you start dealing with fractions. From there, then, we're just going to plug in m is equal to 6, so R is equal to 4 times 36, and then 3 over 20. And then you can start simplifying this stuff too. So that can divide into that and give me 12. This becomes a 5. This becomes a 4. So I end up with 48/5. That's what R is. Ta-da! Now the only other piece that I just realized I don't have an example of, which I'll do right now, is one where we'll see, and I'm just going to set this one up. Let's say Y varies jointly with X and the square of W. Okay. When it says, oops, jointly, this is basically jointly, like together. And this is, we're going to do this directly. So that means that the setup would be Y equals K, and then you'd have X, and you'd also have W squared out here. Okay, so if you see the phrase jointly, that means that the two variables, the multiple variables that they're talking about, are all going to be multiplied together. Real life. Resistance in ohms of a platinum wire temperature sensor varies directly. Okay, so we've got, just lost a pen. The resistance of a platinum wire varies directly as the temperature in degrees Kelvin. So now I've got R is equal to some constant that we don't know yet times T for temperature. Okay, so this is T. This is going to be R for resistance. So now you're just going to plug in for information. So if the resistance is 646 ohms when the temperature is 190, what's the resistance at the temperature 250 Kelvin? So your constant here of resistance is going to be 646 over 190, which if you reduce it, now again, with all these things, leave them in fractional form, particularly if the decimal's messy, because you can get so much of a better answer. In this case, it's just 3.4, so we're okay. So our equation shall be resistance is equal to 3.4 times T, temperature 250 Kelvin going here, so R is going to equal 3.4 times 250, which is 850. And again, please make sure you use a nice label. Okay? So again, know the general setup, find the constant. After you find the constant, go through and plug in the information, and check out to see what they're asking for. Last example, federal government. This is, by the way, how I found out I was almost clinically obese. At one point, the federal government has developed a body mass index, BMI, to determine ideal weights. A person's BMI is directly proportional to his or her weight in pounds. So a person's BMI directly proportional to weight, so we'll call that W, and in pounds, and inversely proportional to the square of his or her height. So it's going to be H squared. So before we even look at anything else, we're going to talk about BMI is going to be some constant that we don't know yet, times the person's weight divided by their height squared. Now please notice they're saying height in inches. So down here when they say 6 foot tall, that's actually 72 inches. So when we start pulling this together to figure out what the constant is, what we're going to do is we know our BMI. The BMI here is this person has a BMI of 24. Is equal to your constant. We have this weight of 177 pounds over 72 squared. So when I multiply this out, multiply through by the reciprocal, and so I'm going to end up with 24 times 72 squared, 77. you get a constant of 702.9. I actually think it's 700 even, if I remember correctly, but I will check. So now we're going to use that constant and say, what's the BMI to the nearest whole number of a person whose weight is 130 pounds? So this number, again, remember, goes here. Let's go ahead, actually, round it to 703. So 703 times somebody's weight divided by their height squared. So in this case, I have the constant of 703 times their body weight of 130 divided by 5 foot 6 inches is 66 inches, so squared. And that's going to equal, and again, they say right into the nearest whole number. So you get 703 times 130. Anybody beat it yet? Beat my plugging in yet? It's going to be equal to a body mass index of 21. And as you can see over here, just for curiosity's sake, healthy BMI is considered 19 to 25. Just because I'm going to guess some of you may want to know. So that's how you do that. Now, in terms of the rubric here, the rubric for direct variation is for basic stuff. You're going to be doing variation equations from a situation involving a single relationship. So it's either going to be two variables. It's either going to be direct or indirect, and then you're going to be able to evaluate the situation based upon that. So in other words, here's the situation. Write the equation, and then give me what's going on. 5.0, you need to do the 3.0 level stuff. Plus, then you're going to have to deal with variables where you have higher powers, and or there's going to be multiple variables that you're going to have to deal with. And then again, pull that out of a situation and go from there. As always, if you have any questions, call or text me. I'll see you in the classroom.